Hi and welcome to MSc. In this video we're going to be looking at formal charge. So formal charge is a method of determining the most likely bonding structure when there are multiple ways to place the valence electrons in a Lewis formula. More than one way to draw it. In the method of formal charge, the atoms in a molecule are assigned a charge. We assume that all bonding pairs are shared equally, so we're not as interested at the first pass when we enter things into a formula as to the electron negativity. Some common scenarios where this shows up, where you can reasonably draw the structure in a couple of different ways, are where we have multiple locations for double and triple bonds, as well as verifying that we do in fact have an incomplete or an expanded octet. So to verify those scenarios that is the way to draw it, formal charge can be used as a tool. So formal charge looks at the difference between the number of valence electrons when the atom's just on its own minus the number of electrons assigned to the atom in the Lewis formula. And we look at the difference. So if it's a positive formal charge, that means it had more electrons in its control originally than it does in the diagram. If it's a negative formal charge, that means now it has more electrons in its control than it did originally. Generally, a negative formal charge will be found on more electronegative atoms. So here's the formula summarized, and let's break this down. Fc is clearly the formal charge. This V value is the number of valence electrons in the unbonded atom, right? Number of valence electrons. N, which is sometimes written as L for lone pairs, is the number of non-bonding electrons. So N or L can be used there, and that's just fine. And the B value is the number of bonding electrons that are connected to the atom. And because they only have partial control, we're going to divide that by 2. Again, we're not worried about electronegativity at this stage here in the formula. So this calculation needs to be performed for all atoms in each proposed version of the Lewis formula. So if you have 2 proposed versions, you need to do it for all atoms in both versions. If you had 3, you'd do it for all of them in all 3 versions of the Lewis formula. The sum of the formal charges on all the atoms in a formula should equal 0 for molecules because they're uncharged, and should equal the charge on the ion for polyatomics. So if we're looking at a polyatomic ion that has a charge of -2, like sulfate, adding up the charge on all the oxygens and the sulfur using the formal charge formula should all add to -2. Once we've calculated the formal charge, we need to figure out what that means. So to determine the most likely formula, we look first and foremost at the Lewis formula with the smallest range in formal charge values, and that's the one that's preferred. We'll see this in an example coming up. The second piece is that negative formal charges should be placed on the more electronegative atom, as I've mentioned before. So here's an example. A really common example that you'll see is this sulfur dioxide. And there are 2 ways of drawing this out. So let's go through this here. We know that sulfur has 6 valence electrons, and there's 2 oxygens, and each of them have 6 valence electrons. So this is actually 6 times 3, which is 18. So I'm going to place 18 electrons in these diagrams. So one option that we can have is you can have sulfur with a double bond to an oxygen and a single bond to an oxygen. Sulfur can have a lone pair, as can this oxygen have 2 lone pairs, and then this one will have 3 lone pairs. Again, you can use X's or dots for the lone pairs, or you can draw lines themselves. So that's one option, and you might say, well, this is actually a resonance structure here, because there is an identical one, because I could place that double bond on either one. And they really are identical options. I'll draw this one with the lines for the lone pairs so you can see the difference. We would have this one here with the 3, and now this one here on this side with the 2 lone pairs. All of these obey the octet rule in this scenario. When I do the formal charge calculations here, I don't need to do it for all of these and all of those, because they really are essentially the exact same structure. The other option I'll draw over on the other side here, and I'll try to keep them separate to avoid confusion. The other option you can come up with is two double bonds coming off the sulfur, and both oxygens with just 2 lone pair each. If you add all this up, you'll realize that this is not quite enough electrons in total. 2, 4, 6, 8, 10, 12, 14, 16. 2 more here on the sulfur. This scenario does have an expanded octet on the sulfur. So that might seem less likely, having an expanded octet versus a scenario that doesn't have an expanded octet. Let's go through the calculation to see which one of these is more likely. So when we're doing this, as I mentioned, because these are identical, they're just drawn with the bond in an opposite spot. We don't need to do both of them, but we do need to do both oxygens. I'm going to label this oxygen A, and I'm going to label this oxygen B when we go through this. So let's calculate the formal charge here for oxygen A. So number of valence electrons for an oxygen is 6. Subtract the non-bonding electrons. Well, I have 4. And we're going to subtract the bonding electrons. Well, I have 4 bonding electrons, 2 from each bond, and I'm going to divide by 2. So 6 minus 4 is 2, minus 2 equals 0. Okay, I'll try it again for oxygen B. So again, oxygen has 6 valence electrons. This one has 6 non-bonding electrons, and it only has 2 bonding electrons, and it controls half of those. So 6 minus 6 is 0, and minus 2 over 2 is negative 1. And I'll now do the sulfur as well. I don't need to label it differently because there's only the one sulfur. Sulfur has 6 valence electrons. In this case, it has 2 non-bonding, and it will have 6 bonding electrons, and it's in charge of half of those. So 6 minus 2 is 4, minus 3 is 1. This leads to a difference in formal charge, a max difference here of 2, right? There's a range here of 2 between the maximum and the minimum charges. Notice that oxygen is more electronegative, so it does make sense that the negative 1 is attached to it and not the sulfur. So that seems reasonable. Let's try the same thing on this other example here. Notice here I don't really need to label my oxygens 1 and 2 because they're identical here. They both have the same bonding and lone pair structure. So I can look at the formal charge of oxygen in this structure. Again, 6 valence electrons in oxygen. Each of these have 4 non-bonding or lone pair oxygens, and each of them also have 4 bonding electrons, and we're going to divide by 2. And so 6 minus 4 is 2, minus 2 is 0. All right, and the formal charge on the sulfur. So sulfur has 6 valence electrons, minus the 2 non-bonding ones, minus 8 over 2, because it has 8 bonding electrons here, and dividing by 2 because it controls half. So 6 minus 2 minus 4 is 0. So the change here in formal charge from maximum to minimum is 0. And that means that this version here is actually the preferred structure. It has a lower difference in formal charge from maximum to minimum than this resonance structure here. So here is an example where we've used formal charge now to identify that, hey, we don't have this scenario. More than likely, we have this scenario here with, even though it's an expanded octet, it generates a formal charge difference of 0. It is the preferred structure. I hope this quick run through of formal charge has been helpful. If it has, please consider liking this video and subscribing to the station. And as always, thank you very much for listening and watching.